more part, and then we can finish solving it, and we'll be done with it. In part 2, we are asked for the speed of rotation of the disk. So find the speed of rotation of the disk, and the problem also states that the moment of inertia for a disk is 1/2 mr squared, which is 1/2 times your mass times the radius of the disk squared. So 1/2 mr squared. Let me add in the exponent, and awesome. So this is going to save us a lot of time when we solve this problem, as there's going to be no integration required or any of that fancy stuff. So let's go back, and we should look at the problem, and we see that we have the disk is being pulled on by the string, and the disk has moved distance L, and the hand has moved distance H. So we also notice that the disk is rotating. As you can see here, the disk has started off in one position and is now rotated over. So when we solve this problem, we're also going to be applying the energy principle as well. In this case, we're going to have the translational kinetic energy, and we're going to have rotational kinetic energy. And when you have both of those and you add them together, the changes in the kinetic energy and the rotational and the translational kinetic energy, we get work. So this is going to help us gain some insight on how we're going to actually go about solving this problem. So let's go ahead and write that down. So change in K-trans, your translational kinetic energy, plus change in K-rot, your rotational kinetic energy, is equal to the work done on the system. So from before, we discovered that the change in your kinetic energy, translative kinetic energy, is equal to work, right? So we found that this was negative FL. This is going to be something that we can then take and substitute into our equation for this problem. So your change in K-trans is equal to negative FL. And then we got to add in your change in rotational kinetic energy. So let's see what's going on here again. We're given a moment of inertia for this, 1/2 mr squared, and we have the formula for the change in rotational kinetic energy, which is 1/2 I omega squared. Now, what does that really mean? So what that means is, with 1/2 I omega squared, so change in K rotational energy is 1/2 I W, or omega as we like to call it, squared, is equal to work done, and in this case it is force times the distance, and that is FH. This is different than before. As you see, this is the force done by the hand, F times H. It's not the translational speed of the disk deal that's going on here, so we're not really concerned with the speed that the disk is going. We're concerned more about the force being applied for the hand. So what's going on here is there's an important concept which I should have mentioned earlier, is that there is a thing called the point particle system, which will essentially take everything in the system and just like squish it down into this one tiny little point, okay? And from there, we're just gonna consider everything at this tiny little point. And when we do that, we can then find the translational speed of the disk. Now, after we do stuff with that tiny little point, we can then apply it to the entire system. So this whole thing about the point particle system allows us to, since we shrink it down, we have to apply everything at the radius of our center of mass. So that's, again, that would be the center of this disk right here. And after we finish doing stuff with the point particle system, we can then take it and apply it to a real system, which is what we do to figure out the rotational speed. So for the real system, we know that you're changing kinetic energy, like all the changes in energy are just going to be like the same. So energy is always conserved according to the law of conservation of energy. And that just states that the final energy is equal to your initial energy. And similarly, like you're changing your kinetic energy final is your kinetic energy initial. But now with this real system, we need to make sure that we take into account all the changes in energy, not just the translational change in energy. So there's different kinds of energy, like chemical energy, which we don't have here in this case. We also have rotational energy, as we can see here, and that's the main one that we're going to be focused on. So applying the energy principle again, we're going to know that the change in our kinetic energy in the translational direction, so the change in translational kinetic energy plus our change in rotational kinetic energy is going to be equal to our work, because we're now taking into account all the different kinds of energy that's affecting our system right now. So let's go back to our Word document and continue working through this problem so we can continue and figure it out. So you're changing your rotational kinetic energy, as I said earlier, is 1/2 IW squared. That's because your final kinetic energy and final rotational kinetic energy is going to be 1/2 IW squared, and if you see initially in the problem, there's no rotation on the disk. So that's why it's 1/2 IW squared. And we have to now add in our work. So equals F times H, the force applied on the system, plus the distance, times the distance over which the force moved from the hand. Again, we're taking into account the hand and not what was going on with the disk, as we were in the point particle system. So this is the real system. Okay? So from here we can continue working and solve for W. So we can add FL. We can see that 1/2 IW squared is equal to FH plus FL. Now the next thing we can do is multiply by 2, and we can group together the FH and FL terms. So this will leave us with the term IW squared equals F times 2F and 2 times F times, this is going to be 2F H plus L is going to go in here because we factored out an F. And then from here, what we can do is we can divide by I, leaving us with W squared equals 2F times H plus L divided by I. Let me remove that I real quick. And then finally, to get us our final answer, we're going to take the square root of this quantity, and then we get that is the square root of 2F H plus L over I is our final answer. Thank you for watching, and I hope you've learned a lot about how to calculate the speed of rotation and how to calculate the change in translative kinetic energy. Thanks again.